In this presentation, I'm going to introduce uncertainty, where we need to consider uncertainty in our lab and the lab reports, and most important is how does uncertainty propagate. By propagate is, I mean how the uncertainty goes from the uncertainty of the data to the uncertainty of the result. So what is uncertainty? When you see a measurement like we're showing here, 70 plus minus 5 kilometers per hour, we say 70, the number in the middle, is the best guess of this speed of the car, or we sometimes call it the value. This plus minus 5 describes how much the number can fluctuate, or it describes a range. 70 minus 5, 65 kilometers per hour, to 70 plus 5, 75 kilometers per hour. So it describes a range. This 5, half of the range, is the uncertainty of the speed. The true value is not known. We don't know whether it is not exactly 70. So we don't know the true speed, but it most likely lies within this range described by the best guess and the uncertainty. This how likely, you don't need to worry. If we are doing statistics, you can, for what they call a normal distribution, but that needs lots of data. You can define this likelihood well, but in our physics labs, as long as you say it's likely that the value is within this range, it's fine. You can be more conservative and assign a bigger uncertainty, or you can be a bit aggressive and say I'm quite sure, so I would like to assign a smaller uncertainty, and they're both okay. So I'm going to introduce the concept of relative uncertainty. The absolute uncertainty is the uncertainty we have been talking about. That 5 kilometers per hour in the previous slide is the absolute uncertainty. One thing that's most important is the absolute uncertainty and the value, or the best estimate. They have the same units. But by the uncertainty, or the absolute uncertainty itself, you cannot tell whether that is a big uncertainty or small uncertainty, or how good your measurement is. For example, 1 meter. If you say the uncertainty is 1 meter, if you're talking about the measurement of a room, of our lab room, it is a fairly big uncertainty. With a meter stick, you can do easily better than that. But if you're talking about, distance to the moon, which is like 384,000 kilometers, then 1 meter would be a very, very small uncertainty relative to the value. So to describe how good the measurement is, or the precision of the measurement, you want to calculate the relative uncertainty. You take the absolute uncertainty and divide it by the value itself. So here for this measurement, 70 plus minus 5 kilometers per hour, the relative uncertainty is 0.0714. And quite often, this is the relative uncertainty. It has no units. Quite often, you would convert that to a percentage, multiply by 100%, you get, and round off to 7%. So relative uncertainty and the percentage uncertainty are the same thing. It's just the percentage uncertainty is the relative uncertainty presented in the percentage form. There are two things that we should remember. One is the absolute uncertainty has unit the same as the value, but relative uncertainty has no units. And the other one is it's easy to convert between the two. You take the absolute uncertainty divided by the value, you get the relative uncertainty. But in our labs, most often we are doing it the other way around. You find the relative uncertainty first and then multiply by the value to get the absolute uncertainty. So where do we have to consider uncertainty in our lab report? Our lab report consists of 7 sections. Purpose, no uncertainty. Apparatus, no uncertainty. Data, yes. So when you record data, you must decide the uncertainty at the same time and record it. How to decide the uncertainty is a more complicated topic. We'll look at it in our first lab. Calculations. This is where you use the best estimate of the data or the values of the data only to calculate the result. So no uncertainty should show up in calculations. The fifth one, uncertainty analysis. Yes, here is when you do uncertainty propagation to find the uncertainty of the result based on the uncertainty of the data and the propagation rules. Conclusion, yes, you must report result with the uncertainty. And that uncertainty is, you calculate that in the uncertainty analysis. Discussion, yes. First, you compare your result to a reference number to see if they agree within uncertainties. And also you discuss like where the uncertainties come from, how to reduce them. Now we move on to the most important part of today's presentation, which is uncertainty propagation. If you have done 1118 with us, you know in 1118 you don't report the uncertainty of the result explicitly. You just report your result with sig figs. Those are determined by the sig fig rules. And now we no longer have sig fig rules. We have to report our result with uncertainty, and the value of the result must match the decimal places of the uncertainty. So here, to get the uncertainty of the result, you will need to know the equation that calculate the result in your calculations and propagation rules. The uncertainty propagation rules can be found on our website. So here is the link. So here are the propagation rules. I would like you to remember the rules both in their mathematical forms like this and in their description forms like the rules in words like here and there. This is the rule number 2. And also pay attention that for the mathematical forms, there are different ways to present the rules. One is with the variable z, which represents the result. One is without z. The right-hand forms, they don't have the z in it. Now let's go back to our PowerPoint presentation. The first rule applies to addition and subtraction. The absolute uncertainty of the result, here is delta z, is the sum of the individual absolute uncertainties. It's very important to remember that it applies for both addition and subtraction. So let's look at the examples. I have this bottle of bees, supposed to be 200 pieces inside. So I poured them out and did a quick count. I got small bees, 130 plus minus 3, medium ones, 50 plus minus 2, and the large bees are 20 plus minus 1. So in the calculations, you calculate the result using this summation, and you got 200. And in the uncertainty analysis, you calculate the uncertainty of the result, which is the sum of individual uncertainties, so you get 6. So when you, in your conclusion, you would say the total number of bees is 200 plus minus 6. When you do subtraction, say these bees, the manufacturer says there are 200 plus minus 2 inside, and you pour some bees out, 70 plus minus 7. I did a rough count of this picture. So now you're taking a difference, and you say there are about 130 bees left in the bottle. The uncertainty of this number is not 2 minus 7. It's not 7 minus 2. It is the sum of the absolute uncertainties. So 2 plus 7, which is 9. It makes sense because after you did some action, the uncertainty would increase because you put more uncertainty factors inside this number. So the number of bees left in the bottle is 130 plus minus 9. So that's our rule number 1. Propagation rule number 2 applies for multiplication and division. The relative uncertainty of the result is the sum of individual relative uncertainties. You know it cannot be the absolute uncertainty because look at our example. Adams rides his bike to Langara. The distance is measured, the time is measured. To calculate the average speed, you use distance over time. But to calculate the uncertainty, you cannot add 0.2 kilometers with 1 minute because they don't have the same units. But the relative uncertainty has no units, so you can add them up. You can add delta d over d and the delta t over t together, and the result you have is the relative uncertainty of the result, delta v over v. So calculate this out, get a number, keep lots of digits because you are in the middle of the calculations, and then use this number to multiply by the value to get the absolute uncertainty. Round off the absolute uncertainty and then report that in your conclusion. Well, it's nice to have the relative uncertainty too in your conclusion. It's there in the percentage format, 16%. So 0.05 kilometers per minute is the absolute uncertainty. It has the same unit as the value, and 16% is the relative uncertainty. So remember, you calculate the relative uncertainty first, and then finally you need absolute uncertainty. Next is rule number 3. Rule number 3 is for multiplication by a constant. It's not independent rule because and you can always, because it's a multiplication too, right? So you can actually use rule number 2 to apply to the situation of rule number 3. It's just more convenient sometimes that you can use rule number 3 directly. When z is kx and k is a constant, by constant I mean that k has no uncertainty. Then you can either calculate the absolute uncertainty, delta z is k times delta x, or you can calculate the relative uncertainty, delta z over z is delta x over x, and there's no k here. You may wonder, where is k? K is gone because delta z over z, if you apply rule number 2, that will equal to delta k over k plus delta x over x. But because delta k is 0, delta k over k is also 0, so it is gone. So you're left with only the relative uncertainty of x. The two equations, although one has a k and the other one doesn't, they actually give you the same result. You can see that from this example, okay? Back to the same bottle of bees. Each bottle is 200 plus minus 2 bees inside, and that is 1% uncertainty, relative 1%. If you buy 10 of them, how many B's do you have? Well, it's 2000. To calculate the uncertainty of the result, if you use the absolute uncertainty, then you use delta Z equals K delta X, and that is 10 multiplied in 2, so you get 20. If you use relative uncertainty, you're going to say delta n over n equals to delta n1 over O n1, which is again 0.011%. And you use that relative uncertainty multiply n, you get 0.01 multiplying 2000, you get 20, you also get 20. So it doesn't matter which form you use, which form of rule number 3 you use, you're going to get the same result, 2000 plus minus 20 B's. Sometimes it's more convenient to use rule number 3, but if you never use rule number 3, you always just use rule number 2, you're actually okay. Rule number 4 applies to powers. So the rule is, if z is x to the nth power, then there's no absolute, no rule for absolute uncertainty. You just have delta z over z is n times delta x over x. If n is negative, okay, like x to the minus 2's power, you put absolute value sign outside n. So here you see it's the relative uncertainty get n times bigger. Don't mix up this exponent and constant. When do you multiply the relative uncertainty by a factor? Is when you have an exponent. You have to put that exponent in front of the relative uncertainty. So here is an example of applying rule number 4. Area is the side squared, and delta A over A, that's the relative uncertainty of the area, is 2 times delta little a over A, and you calculate that out and then multiply by the area to get absolute uncertainty. So here are the 4 propagation rules. Rule number 5 on your sheet. We are not going to talk about it today because we don't really need it. 1, 2, 4 is enough. 3 and 5 can sometimes make your calculations easier. So we are going to skip rule number 5, and we are going to introduce that later in our lab. Finally, this is a note to these rules. They do apply to many variables. You don't have to have only 2 variables, but if you have calculations mixed together, then you have to be careful. If all the calculations are plus minus, like the first example here, then you don't need to worry. Just add the individual absolute uncertainties together and you get the absolute uncertainty of the result. If they're all multiplication or division, yeah, the same thing, only this time you have to deal with relative uncertainty. If it's multiplication, division, and exponent, then you can do them this way. Apply the rule number 2 first, and then rule number 4. Here, you see that everything is multiplying or dividing. So you have delta z over z. You can do that because both rule number 2 and 4 are for relative uncertainties, right? So it's 3 times delta x over x, delta y over y. You might as well put delta 4 over 4 there and treating 4 just as a variable for now. And the square root of v is, you should have delta square root of v over square root of v, but that, if you apply rule number 4, will equal to half delta v over v and delta w over w. So that's it, but after that you can simplify this because delta 4 is 0. 4 is a constant, it has no uncertainty, so you can simplify this propagation equation. So here are all my introduction on the uncertainties and uncertainty propagation. Next we are going to practice how to apply these rules.